Torque of the electrical dipole in the uniform electric field. The uniform electrical field is represented by parallel lines, and these parallel lines represent the direction of electric field. Its magnitude is constant at everywhere. Now, if we have a dipole AB whose length is small d, negative charge is at point A and positive charge is at point B, the direction of dipole moment of this dipole will be from negative charge to positive charge, that is from A to B. Now, if the angle between electrical field and dipole moment is theta, then the force at point A will be equal to Q into E towards left, and at B Q into E towards right. So these two forces are equal in amount, but they are opposite in direction. So net force on the dipole will be 0, since QE is equal to QE, but they are in opposite direction. So net force on the dipole is 0. It means the dipole is stationary and it will not have any translation motion. The translation motion is only possible if the force exists on a particle. Now, since QE and QE, these two forces are in opposite direction, but they are at a distance. So this will try to rotate the dipole. The torque for this rotation can be calculated. Now, torque is equal to the force multiplied by perpendicular distance between the two forces which are in opposite direction. So the torque will be equal to force is Q into E multiplied by the perpendicular distance which is equal to BC. Now BC angle from the triangle BC is equal to D cos theta, D sin theta, sorry. It is equal to D sin theta. Therefore, torque will be equal to Q into E D sin theta. Q into D is magnitude of dipole moment, which is the product of charge of any multiplied by distance between these two charges. So we can write this Q into D as P. So torque will be equal to E into P sin theta. Now it will give the direction, because torque is a vector quantity. So torque, which is represented by tau, then vector tau is equal to Pe sin theta into n cap, or we can write torque is equal to P cross E. So torque is vector product of dipole moment and electrical field. Now, what will be the direction? The direction of dipole moment and direction of electrical field is subtended at angle theta. Then the direction of torque will be perpendicular to the plane containing P and E. And direction is given by right hand rule, which is applicable for the cross product. So the direction of torque will be perpendicular to the plane of P and E in the downward direction. Now, what will be the torque at different angles? If angle theta is equal to 0, then torque will be equal to Pe sin 0, which is equal to 0. Means the dipole will be at rest, or this condition is stable condition. second point, when theta is equal to 90, then torque will be equal to P sin 90, which will be equal to P into E, which is the maximum value of torque. Third point, when theta is equal to 180, torque will be equal to P sin 180, which will equal to minus P into E. So the dipole will be in the unstable condition, and it will try to rotate so that its theta will become 0. So what will be the unit of torque? The unit of torque will be equal to Newton into meter. But torque is a vector quantity, although the unit of work is also Newton into meter. But torque is a vector quantity where work is not a vector quantity, that is a scalar quantity. Now we can also define dipole moment in terms of torque. Now if we consider that the force, if we consider that electrical field is 1 Newton per coulomb and theta is equal to 90, then torque will be equal to P. So we can say that torque of the dipole will be equal to dipole moment if it is placed in a unit electrical field and the angle subtended by the dipole is 90 with the electrical field. So this will be the end of the chapter 1. Now we will start the chapter 2. Now the term, what is the electrical flux? Now what do you mean by the electrical flux? Now if the direction of electrical field is like this, and we have some area S which is perpendicular to this electrical field, then all the electrical lines of force or electrical field lines will pass through it. Then the flux will be maximum, and flux maximum, phi maximum will be equal to electrical field multiplied the surface area of the area. Now if the angle subtended by the area is not equal to 0, so we consider this case, then this is the area, and the area vector is in the direction perpendicular to this area, and this will be the direction of S. This is the direction of E. So angle subtended between electrical field E and S is, vector S is theta. So the component of area in the direction of field will be equal to S cos theta. Therefore, the electrical flux phi E will be equal to E into S cos theta, or this is equal to E dot S, or the maximum value of this will be equal to E into S when theta is equal to 0. Now in case if we have a large area, we can divide the area in number of small elements, and these elements are shown here. Now we take any one element. For this element, we have electrical field in this direction. The area vector which is perpendicular to this area is in this direction, and theta is the angle subtended between electrical field and area vector ds. Then what will be the electrical flux? The electrical flux due to this small area is d phi E is equal to E vector dot ds vector, where ds vector is area vector of this small area ds. So if you want to find the total electrical flux due to this entire region or entire area, then we have to take the help of integration. Then total flux of this area will be equal to phi E will be equal to surface integral into E dot ds. So in this way we can find the total electric field due to any area. Now what is the electrical flux? Electrical flux is a scalar quantity. Its unit SI unit is Newton into meter square per coulomb or volt into meter. The dimension is MLT minus 2 foot divided by charge that is equal to A into T. This will be equal to into L square area. So this will be equal to M power 1, L ka power 3, T ka power minus 3 and A ka power minus 3. So this will be the dimension of electrical flux. Now what is the electrical flux? Electrical flux is the strength or number of the electrical field lines which are passing through this area. Now we can find the numerical value of electrical flux when electrical field and the area of the area is given. If the electrical field is 50I plus 30J volt per meter and the area vector is equal to 100G meter square, then the flux, electrical flux phi is equal to E dot ds. So E will be equal to 50I plus 30J dot 100J. So by scalar product we will get 3000 volt into meter. So in this way we can calculate the electrical flux. So this is all about the electrical flux. So if the electrical flux is more, then electrical field will be also more. So density of electrical lines of force or electrical field lines is measure of electrical field. Now if we are having a conductor and we will give the charge, then the charge will be on the upper surface of the conductor. So we can have the continuous charge distribution. Now it will depend upon what is the dimension of the conductor. If the conductor is linear, then it is in one dimension. If the conductor is a plate, then it is in the two dimension. And if the conductor is in three dimension, then the distribution will be in different ways. If we give the charge to the conductor, then the charge will be distributed on the upper surface of the conductor. Now, since the charge is quantized and when the charges are similar, there is a repulsion between these two charges. So, the one charge cannot diffuse into another charge, but they will be repelled by each other. And in the case of linear conductor, then the charge density for the linear conductor is linear charge density represented by lambda. And lambda will be equal to total charge on the conductor divided by the length. So it will be equal to Q bata L and the unit is coulomb per meter. Second, if the conductor is in the form of plate or it is in the two dimension, then surface charge density will be equal to sigma, which is equal to total charge on the plate divided by the area. So its unit will be equal to coulomb per meter square. Now third type of the charge, which is continuous and distributed on the volume, then the volume charge density will be equal to rho, which is equal to the charge on the entire volume divided by the volume. So it will be, its unit will be Q bata volume, that is equal to coulomb per meter square. Q. So now we can find the electrical field due to the different continuous charge distribution. It means if the charge distribution is linear, it may be charge distribution is on the surface and it will be charge distribution on the entire volume. So what will be the procedure? The procedure will first, we will consider a small element, whether it is of the length or it can be of area or it can be wood. Then the charge on that small element will be equal to the charge density multiplied by its area or length or volume. Then third point, we will consider a point P, where we have to find the electrical field. Now this small element will work as a point charge and we will find the electrical field at point P due to this small element by Coulomb's law. The total electrical field due to the entire conductor can be found by integrating so this procedure will be adopted by us. First we will calculate the electric field due to linear charge distribution. Now we consider this is a linear charge and the charge density on this linear conductor lambda, which is equal to the charge divided by length. Now if we consider a small element dl on it, then the charge on this small element dl will be equal to lambda into dl. Now at the center of this small element O, and we consider at point P, which is the point of observation, where we will find the electrical field. The electrical field at point P due to the charge of this small element can be calculated by Coulomb's law. So by Coulomb's law, the electrical field dE due to this small element will be equal to 1 by 4 pi epsilon 0 lambda into dl, that is the charge of the element divided by r square into r cap, where r is the distance between the center of the element and the point P. So electrical field for entire linear conductor will be equal to 1 by 4 pi epsilon 0 into lambda, then line integral dl by r square into r cap. So in this way we can find the electrical field due to entire length of the linear conductor. Now second, if you want to find the electric field due to the surface charge distribution, we take this surface and the charge is distributed all over the plate and the charge distribution is uniform. So the charge density on this surface will be have space charge density is sigma. We consider a small element whose area is ds. Then charge on this small area ds will be equal to sigma into ds. Now we want to find the electrical field at point P, which is at a distance r from this area. Then the electrical field due to this small element dE vector will be equal to 1 bata 4 pi epsilon 0 sigma into dH bata r square into r cap using Coulomb's law. Now if we want to find the total electrical field due to the entire surface, then we have to take the surface integral. Then total electrical field will be equal to sigma bata 4 pi epsilon 0 surface integral around the total surface dS bata r square into r cube. So in this way we can find the electrical field due to a surface charge distribution at any point. Now third, we will find the electrical field due to volume charge distribution. If this body is a three-dimensional body, then the charge on this body is distributed in three-dimensional. The charge density is volume charge density, which is equal to rho, means the total charge divided by total volume. So if we consider a small volume of this element, this small volume element, then its volume is dV. Then the charge of this small volume will be equal to rho into dV. So this will be charge. Now using the Coulomb's law, we can consider the electric field due to this small volume at this point, which is at a distance r from this volume. Then the electrical field dE due to this small volume will be equal to 1 bata 4 pi epsilon 0 rho into dV. That is the total charge of the volume divided by r square into f using Coulomb's law. Then if you want to find the total electrical field due to the entire volume, then we will have to take the volume integral. We have taken line integral when the conductor was linear. We take the surface integral when it was a two-dimensional, and when it is the three-dimensional, then we will take a volume integral. Then electrical field will be equal to rho divided by 4 pi epsilon volume integral dV bata r square into r cube. So in this way we can calculate the electrical field for linear conductor and surface and the volume. Now we will use this method to find the electrical field due to a ring which is uniformly charged. If we take a ring and whose radius is capital R, the charge given to this ring is capital Q, then this charge will be uniformly distributed on this ring. The charge density or linear charge density on the ring lambda will be equal to total charge Q divided by 2 pi R, which is the circumference or the length of the conductor. If capital R is the radius of this ring and O is its center, and we want to find the electrical field at point P, which is at a distance x on the axis. For this, we will consider two elements, one is at A and another at B. The length of this element is equal and they are in opposite direction. They are equidistant from P, means AP is equal to BP. The angle subtended by AP and BP with the axis is theta. So the charge on the small element at A or B is dl multiplied by lambda. So we will apply the Coulomb's law and find the electrical field at point P due to these small segments A and B. Then for A segment, electrical field will be equal to 1/4 pi equal to 1 bata 4 pi epsilon 0 lambda into dl bata r square, and its direction will be AP. Similarly, the electrical field at point P due to the small segment at P will be equal to dE2 which is equal to 1 bata 4 pi epsilon 0 lambda dl bata r square into PP direction. The magnitude of dE1 and magnitude of dE2, they are equal, but their directions are different. Therefore, we will resolve these electrical field dE1 and dE2 on the axial direction and perpendicular to the axial direction. For the axial direction, the component of electrical field dE1 and dE2 are dE2 cos theta and dE1 cos theta. Both are in the same direction. Whereas in the perpendicular direction, that is YY dash direction, the component of electrical field dE2 sin theta in the plus y direction and dE sin theta in the minus direction. Since the magnitude of both dE1 and dE2 are equal and they are in the opposite direction, so they will cancel each other. Hence, the electrical field will be only in the axial direction, and that is equal to dE1 cos theta or dE2 cos theta. So, if you want to find the total electrical field due to this charge thing at point B, we have to take line integral, and the line integral will be equal to line integral. So first of all, we will find the magnitude of E1, which is equal to magnitude of dE2, which is equal to dE or and cos theta is equal to x divided by r. This is x, this is 2. So cos theta is equal to x divided by r, and r is equal to, by Pythagoras theorem, r will be equal to capital R square plus x square. So, if you want to find the total electrical field due to the entire ring, then this can be found by taking the line integral of either dE1 cos theta or dE2 cos theta. So, total integral will be equal to line integral dE1 cos theta. This will be equal to 1 bata 4 pi epsilon 0 lambda bata r square into x bata r, which is cos theta, into integral line integral dl. The line integral dl will be equal to the entire length of the ring, and which is equal to 2 pi r. Now substituting the value, we will get electrical field for the entire ring will be equal to will be equal to 1 bata 4 pi epsilon 0 into lambda into x into 2 pi r divided by r square into r. So this will be equal to 1 bata 4 pi epsilon 0 x into q bata r square plus s square का power 3 by 2. Since 2 pi r multiplied by lambda is total charge on the ring, hence total electrical field will be equal to 1 bata 4 pi epsilon 0 x into q divided by r is capital R square plus x square power 3 by 2. Now if we consider that the radius of ring is much smaller than the distance between O and P, then we will get E will be equal to 1 bata 4 by epsilon 0 q bata x square, and this is same as if the entire charge is placed at the point O and we have to find the electrical field at P. The direction of electrical field due to the entire ring will be always into OP direction. So in this way we can apply the Gauss law, we can apply the line integral to find the electrical field due to this ring. So this is the end of the lecture. I will give you the details of all this material which I given you on next day.